In this lecture, let's talk about the electric field from a charged area. It's similar to line, but now instead of line charge density, we have surface charge density, eta. It is also defined as the total charge per unit area. Similarly, we are going to break the area into small area, dA. For each dA, it has small element of charge, dQ, which can be represented as theta, the density, times dA. So the net electric field at a point P from the body is then the integral of dE, which is similar to the electric field from point charge, but the Q now we replace it with dQ, which is the density times dA, and we take the integral, so we sum up all the small pieces. And we can also have non-uniform distributed area. Then the eta, the surface charge density, will be a function of x and y. Now let's look at this example. Here we have a circular disk of radius r, big R, which carries a uniform, positive surface charge density, eta. Point P is at the distance x above the center of the disk. So it's similar to the example that we looked at in the previous lecture, but now the ring is filled. And similarly, we want to find the net electric field at point P. Here's a sketch of the problem. Here the disk is now filled. It is similar to the example from the previous lecture, but now we don't have a ring, but we have a disk. On the right, I have a face-on view. So we have the x-axis that is pointing outward. And the way I'm going to break into small pieces is I'm going to take very thin ring at each R. So here's an example. Here's my small piece. The width of the ring is dr. And it has radius r, where the radius of the disk is capital R. From the previous example, we already found the net electric field from a ring. So we can just take the answer from the previous example. When I break the disk up into infinitely small concentric circles, for one ring, dEx is the result from previous example. But note that in the denominator, in the previous example, I have capital R squared, but now the R, I want to take the radius of my small ring, which is small r. So here in the denominator, we have x squared plus r squared to the power of 3 over 2. And the Q here is the charge of this ring. Then, to find the net electric field, Ex, I take the integral of dEx, which is integral of Coulomb's constant times x divided by x squared plus r squared to the power of 3 over 2 times Q ring. But the Q ring is depending on the radius to the ring. If I can unfold this ring, I can get a rectangle where the height is dr. And the length is the circumference of the ring, which is 2 pi r. So Q ring would be the density eta times dA, where dA is the area of this rectangle. So 2 pi r times dr. So Q ring is eta times 2 pi r dr. Then we substitute this back to the integral. We get integral of Coulomb's constant times x divided by x squared plus r squared to the power of 3 over 2. And Q ring is density times 2 pi r dr. And here we are summing up all the rings from when the radius is 0 to when the radius is r, big R. So integral's bound is 0 to r. We can pull out the constant, Coulomb's constant, x, and the surface density times 2 pi. Then the integral r dr over x squared plus r squared to the power of 3 over 2. Integral from 0 to r. Then we can use U sub. Let U equals to x squared plus r squared. then du would be 2r dr. Then this equals, we borrow this 2 to here to complete the du. So now we have pi density times Coulomb's constant times x, integral of u to the power of negative 3 over 2 du, and integral from r equals to 0 to r equals to big R. This is a simple integral. Integral of u to the power of negative 3 over 2 equals to u to the power of negative half divided by negative half. Then we substitute the u back. We get pi density ke times x, then u is x squared plus r squared to the power of negative half divided by negative half from 0 to r. So the x component of the electric field equals 2 pi density times Coulomb's constant times x times 1 over x minus 1 over square root of x squared plus r squared. So I bring the negative sign to switch the order of the bounds. So the net electric field from a disk equals 2 pi surface density times Coulomb's constant times x times 1 over x minus 1 over square root of x squared plus r squared. And this is in the x direction only, so times I hat. Unit is newtons per coulombs. And a quick note, when we have an infinite plane of charge with the surface density eta, we can use the result we just found, but we are going to take the limit as r goes to infinity. So limit as the radius big R goes to positive infinity, which means we have an infinite large plate. So we take the limit of the result, 2 pi density eta times Coulomb's constant times x times 1 over x minus 1 over square root of x squared plus r squared. And this is in the x direction. As the radius r goes to infinity, this term goes to 0 because we have the radius in the denominator. So this equals, we only have the first term left. The x in the denominator can cancel out with the x in front. So we are left with 2 pi, the density, times Coulomb's constant, with Coulomb's constant equals to 1 over 4 pi epsilon naught. So for an infinite plane of charge, the net electric field equals to the surface density, eta, divided by 2 epsilon naught in the x direction times I hat, newtons per coulombs. And that is the end of the lecture. In the next lecture, let's talk about the electric field from a charged volume.